In this video, we're going to be learning about the kinetics of radioactive decay, or how fast radioactive decay happens. So kinetics is probably a new word for you. Hooray for vocabulary. Kinetics is just the study of the speed or rate of chemical reactions. So kinetics is just investigating how fast reactions happen and what factors affect that. So kinetics of radioactive decay is just how fast these types of reactions are happening, is what we're looking at. So radioactive decay processes follow what's known as first-order kinetics. And what this means, so different reactions, different types of reactions can have what we call different reaction orders, but all radioactive decay processes are first order. And what this means is that no matter how much stuff you start with, it always takes the same amount of time for half of it to react. So for all reactions that have first order kinetics, this is true. And this idea of half of our stuff reacting is what we call the half-life. So the half-life is the amount of time it takes for half of the reactant to react. And so what we're saying here is that for first order reactions, the length of a half-life is constant, or the length of all half-lives are the same. And they're independent of how much material you're starting with. So that's not true of other reaction orders. For other types of reactions, the half-life depends on how much you're starting with, that you get a different half-life if you get a longer half-life if you start with more stuff, or a shorter half-life if you start with more stuff, depending on the reaction. So we're not going to talk about any other kinds of kinetics besides radioactive kinetics in this course, so just first order is what we're looking at. So what this means is that every half-life you're cutting your amount of stuff in half every time a half-life goes by. So after one half-life, 50% of your original material remains. After another half-life, two half-lives, you're taking that 50 and you're cutting it in half again. So it's not that after the second half-life it's all gone, it's that 50 is now getting cut in half to 25. After 3 half-lives, that 25 is getting cut in half. 12.5% remains. So on and so forth. So the relationship between time and amount of stuff remaining is logarithmic. And you may not, probably have not, seen logarithms in math class yet. So we're going to give a very brief preview of how logarithms work. So the relationship between time and percent of reactant remaining is logarithmic. So what a logarithm is the inverse function of an exponent. So just like multiplication and division are inverse functions of one another, logarithms and exponents are inverse functions of one another. One undoes the other, essentially. So, for instance, this is where I become a math teacher for like 5 minutes. There's a reason I'm not a math teacher. Let's just say that. If x to the y equals z, we call x the base, y is our exponent. Then log base x of z is equal to y. So what a logarithm is essentially doing is answering the question, x to what power equals z? So that's the question that logarithms are allowing you to answer, that you maybe probably don't have a mathematical tool to answer at this point besides guess and check. Logarithms allow you to do that in one fell swoop. So the most common and probably the easiest type of logarithm to think about is base 10, is where x is equal to 10. And these are so common that if there's no base written, if the base is not specified, it is 10. So, for example, let's look at some that you probably can do in your head. This one is relatively straightforward. 10 to the x equals 100. You could probably solve for x just by looking at this, and you know that 10 squared is 100. 10 times 10 is 100. The way you would solve this in, say, your calculator is using a logarithm. If you find the log button on your calculator and put in log 100, that is solving for x here. So that would be 2, and I would encourage you to try this in your calculator, prove to yourself that it's true. If you find the button that says LOG on your calculator, it's usually written as capital LOG. Doesn't really matter. Most people do it in lowercase, just writing. By calculator notation, it is generally uppercase. But not all of them are, not all logarithms are this straightforward. So like this one, you could pretty easily come up with x is equal to 2, just because you know that 10 squared is 100. But for example, what if we wanted to do, instead of 100, 10 to the x equals 50. So now solving for x is not straightforward because x is not an integer. here. So in the case of base 10 logs, it's pretty easy when x is an integer, when your exponent is an integer. But in this case, it's not going to be. So this is where logarithms come in handy, because you can just punch into your calculator log of 50, and that is going to solve for that exponent for you. And you should find that your calculator tells you it's about 1.699. So for the purposes of this course, if you know how to do logs in your calculator, like if you can find the button and you know where to push it, you're in pretty good shape. I don't need you to have a super deep understanding of logarithms and how they function and all the rules associated with them, because there are lots of different things you can do with logarithms. So base 10 is the most common, but it's actually not the one that we're going to be using here. So don't mind me, I need to give myself a little more space than I did when I was prepping my notes. That should do it, I think. So we're actually going to be using what's known as the natural logarithm, which is a logarithm with a base known as e. So e is a constant. It is an irrational number. I think of it as kind of like pi, but a different value. It's an infinite, non-repeating decimal. And it has an approximate value of 2.718. So kind of like pi, but a different number is how I like to explain it. So we'll be using log base e, which is commonly abbreviated ln for natural logarithm. I usually write it in cursive and script letters just because otherwise the L looks like a 1 and that can get confusing. Once again, in calculator notation, when you find the button for this on your calculator, because it is a separate button, it's either right next to the log button, or sometimes it's the second function on the log button. I'll say ln is the button that you're looking for, is the one that you're actually going to be using most often. So otherwise it functions exactly the same as any other kind of logarithm. If we want to solve, instead of 10 to the x up here, we're doing e to the x down here. If we want to solve e to the x equals 27, we put into our calculator the natural log of 27, and that is going to be equal to x, and we'll find that that is 3.30. So we're going to be using natural logs in the equations that will help us do some calculations related to the kinetics of radioactive decay and half-lives. So we have this set of equations here with an assortment of variables. We have t1 half, which is representing the length of one half-life. So the the lowercase t is always representing a length of time of some sort. So the subscript 1/2 here is specifying it's the amount of time it takes for one half-life to go by. K is something known as the rate constant. Every chemical reaction has a different rate constant. So in this case, for first order reactions, such as radioactive decay, the half-life and the rate constant are related to one another by this equation. And then it's actually the rate constant that shows up in our other equations here. Just t is the amount of time that has gone by in whatever situation you're considering. ln is our natural log, so this is not a variable, it's a function. nt is the amount of sample that remains after time t has gone by. And then n0 is our initial amount of sample. How much did we start with? So these equations allow us to figure out how much material is going to be remaining after a particular amount of time. So note that these two equations are the same thing, just rearranged. You will notice that they include all of the same variables. You are given equations and constants as needed. on all quizzes and tests in this course. So you'll be given all three of these different equations, and I give you both versions of this just because I know you're not super comfortable with logarithms yet. So again, this is just a rearrangement of the same equation, but I give you both so that you can solve them more easily. Essentially, if you are solving for either k or t, you want to use this first one. You cannot solve for something like inside your logarithm function without getting it out of the logarithm function, which means if you wanted to solve for nt or n0, you would literally have to turn the equation into this version first. So we're going to use this version to solve for nt or n0. Again, you can't solve for something directly in the exponent unless you use a logarithm. So in order to solve for k or t, you would have to convert this equation back to this equation, so I just give you both of them. So you don't want to be solving for something inside the logarithm or inside the exponent, you want to be solving for something outside those things. So you'll have both versions, just kind of recognize when to use each one. So at this point, let's take a look at an example. So if we know the half-life of technetium-99 is 6 hours, we can find out what percent of a technetium-99 sample remains after 15 hours. So why don't you pause here and give this one a try on your own before I talk through it. Okay, so with problems like this, I always kind of like to start by taking inventory of like what I know, what I'm trying to solve for, all that good stuff. So I know my half-life is 6 hours, and I know that the amount of time passing that I'm interested in investigating is 15 hours. So that's all I am explicitly told up front. I know that I'm looking for how much is left at time t, so that's what I'm solving for. So I like to notate that as kind of my question mark, that's my end goal I'm trying to solve for. And 0, I'm not given a specific amount that I'm starting with, but I can assume I'm starting with all of it. If I'm looking for what percentage is remaining, I know I'm starting with my whole sample. Initially, I have 100% of my stuff. That will give me NT what percent is remaining. And then K, I also don't know initially, but I can find. If we look back at our equations, K can be calculated just from the half-life. So I know the half-life, and T1 half equals 0.693 over K. So if I rearrange this to solve for K, you can do it before or after subbing in numbers, entirely your choice. K is going to be equal to 0.693 over the half-life, which is 6 hours. So when I plug that in, I find a value for K of 0.1155. Inverse hours. I have a unitless number on the top divided by hours, so 1 over hours, or hours to the minus 1, would be the correct unit on that. Your units for K for this type of reaction are always going to be some kind of inverse time. So if you're dealing with seconds, it'll be s to the minus 1. If you're dealing with hours, it's hours to the minus 1. If you're dealing with years, it's years to the minus 1. Whatever your time unit is. Inverse is going to be your units for K. So now, NT is what I'm looking to solve for. So I want to use this version of the equation. And at this point, I know everything else. I know the value of K, I know the value of T, I know a value for N0, and that's going to allow me to solve for this. So we have e to the minus kt is equal to nt over n0. I can sub in everything that I know. E to the minus 0.1155 times 6 is going to be equal to nt over 100. So this whole expression you'll want to just put in your calculator. Do make sure that you put the entire exponent in parentheses to make sure that it deals with it correctly and doesn't just take the first part as the exponent and then multiply the result by 6, which is not what you're looking for here. Parentheses are your friend. So we can put that whole thing into your calculator and find 0.1768 is equal to nt over 100. So then if we multiply both sides by 100, we find that nt is about 17.7%. And I will say, don't worry about sig figs on these calculations, because the rules for sig figs with logarithms get weird. They're not the same as anything you've learned so far, and I know logarithms are still probably foreign for most of you, so I'd rather you just focus on being able to do the calculations, round to a reasonable number of significant digits. 3 is usually a great choice. But that is all for this video. Thank you for watching.